All right, well, thanks guys for coming. My name is Alex. I work for Self-Through. I'm also here with Div over there. And we'll be here today to talk about balancing infrastructure with optimization and problem formulation. So we both work on Self-Through's data science team, and we deal with these three problems every day. And they're really critical to kind of how you practice data science. So, as I said, the talk is really about how do we think about and practice data science. So here's the outline. The first thing we're going to talk about is what is data science, and then where should we spend our time? And probably have a pretty good idea so far in the title. And then part two gets a little bit more technical in terms of how do we balance these three things at Self-Through, and what are some tools we've made and how we kind of work out. So what is data science? According to Wikipedia, it's the extraction of knowledge from data. That's a pretty vague, almost not very information-packed definition. But it gets you to the right direction. So if you go to Google and image search for data science, there's a lot of these that come up. These are the three different fields. You have hacking, expertise, knowledge, and statistics. And somewhere in the middle is data science. That's not bad. And this is also a pretty good one, right? So data science is made up of kind of these components just broken out a little bit more granular. A lot of the stuff you guys are doing today might have to do with like hacker mindset, visualization, and then the math, statistics, and the advanced computing or distributed computing, these problems. Yeah. And like my question kind of is getting to like the fact that data scientists are generally recognized as being good at structuring problems and solving for and then optimizing them. So a lot of people have said in the past that data science is like the art of optimizing things. Other people kind of say, yeah, but in order to optimize things, you also need to first have identified the problem and been able to structure it well. And so these are things that are really important. We're all kind of in agreement that we do, but something's missing. So what's missing here? And so we mentioned these three things, kind of got 2 out of 3. And so my third one is going to be infrastructure, right? So what is infrastructure? And according to Wikipedia, the best source for definitions, it's the basic physical and organizational structures and facilities needed for the operation of society or enterprise. And I'm going to argue that infrastructure is not only really cool, but also really complicated and very important. So often underappreciated by data scientists. A lot of people kind of just look at it and be like, I don't want to deal with that. And as a result, when you get a data scientist building infrastructure, it oftentimes ends up looking something like this. It's kind of fun to build those. I've done them many times. But they don't last too long, and they lead to all sorts of really annoying problems, I would say. But at the same time, it's something we're intimately familiar with. And it's a mission-critical component of our work, right? So if you guys work in the cloud, like we work in Amazon Web Services all the time, we kind of live in our environment, in our machines. We're very familiar with the ins and outs of all of these little components. There's a lot of components. Components of a really good infrastructure, in my opinion, look kind of like this, right? So you have tons of machines. Machinery comes in the form of like Amazon virtual machines, right? If you have a data center, those are bare metal hardware that oftentimes run operating systems. And there's things called containers. Docker is a really good example of one of those. And when you have a lot of things, you basically have a lot of these little nodes in a space, you need to coordinate them in different ways. And that's where all the complexity for this arises, right? So you need coordination, redundancy, fault tolerance, and there's a really good theorem called the CAP theorem that talks about consistency versus availability and partitioning, and you can never have all three. They prove it in this paper, but you can have two of the three. So that's something worth checking out. And because of all of these needs, you kind of get a whole bunch of different areas within this infrastructure need that you kind of need to figure out before you can build a data science platform like we did for Salesforce. And sometimes you need to reinvent the wheel. Most of the time, stuff's already there, just try to find it and use it. So resource allocation, right? I don't know how much I want to go into these slides in specific, but resource allocation is the idea of kind of you have this box of resources, right? Maybe RAM on this plane and CPU on this plane, and you just have these different tasks that are different sizes. This one's a big one, this one's a little one. And the idea is how do you efficiently pack that box so that you maximize the resources you have. The idea being that you don't have unlimited resources when you have space. And then there's all these problems that come into that with like spare scheduling, dominant resource fairness, different kinds of ways of managing the allocation of resources. Ad companies are really good at this, right? This is their business model. And then control strategies. So there's this whole branch of computer science called control theory, right? That deals with like signals and feedback loops. And so thermostats, PID is a thermostat algorithm that I'll actually talk about later. Auto scaling, which is a huge problem that a lot of people deal with. Things like that. Communication algorithms. So there's a lot here. If you've ever heard of a Zookeeper, right? And Console and CD, they all have their different ways of kind of, actually I don't know about etcd. They all have different protocols that they use to coordinate with each other. Mesh networks deal with this a lot. Oh, great. One second. And then there's, the things like monitoring. So the problems here could be anomaly detection and visualization. Actually, a lot more than that. But, and then data storage. So there's different ways to store data, and then for each way, there's about 1 million database options, right? Relational graph, key value, document store, so on and so forth. And the point here is that there's 1 million tools, and you kind of just need to use more or less one from everything and probably a lot of other things. And so when you think about what is data science, right? It's this idea that, yes, you have the problems you want to solve. Yes, you have the problems you want to optimize. And yes, you have the infrastructure that you need to be able to do all of this. But when do I choose which area to work in, and how do I know when to do that? And I don't know how to answer that for you. But the point is, it's really important and I think interesting to think about data science from this perspective, because it's a very practical way to think about what you're doing. So, going on to part 2, right? The 115, not bad. So the question here is, how do we do this at SailFree? And so before I kind of go into that, maybe I'll just tell you a slide about what we do. So SailFree is a personalization company. We do marketing communications. These are some of our customers, right? Mashable, The Economist, Birchbox, a lot of other brands. And basically, we're what we're called a business-to-business company. So our customers are businesses, and then these businesses have a customer, or B2C companies. These businesses have people who are their customers. And we sit in between the communications that businesses have with their customers and try to make them personalized better. Right, and our goal is to maximize this concept called lifetime value of a customer, so that our customers do well, the customer does well, our clients do well, and as a result, we're also doing well. Lifetime value is a really interesting term because the idea of it is that we want to keep a customer as long as possible. To do that, we need to make sure that they're not unhappy with the way that you've been communicating with them. So to deal with this problem at SailThrough, we've built a platform called Sightlines. And Sightlines generates predictions about what people are going to do in the future, what customers are going to do in the future specifically. And here's an example use case of some of the predictions that we make, right? So I don't know how well you guys can see this, but the probability of making a purchase in 30 days, 24 hours, 7 days, expected order value if they make a purchase, the revenue we'll make from them in 30 days, and also going out to the future, we're releasing that soon. And then a couple other ones dealing with messages, like whether they're going to opt out, how many messages they're going to receive, what their open rate is, and stuff like that. So, right, I didn't know this. Okay, so the general gist of how Sightlines works. This is a very simplified view, and we'll go into some specific details later. But basically, you have this problem where you have this data stored in Mongo in a nested JSON structure. And the data looks like this. This is actually one of our users, or one of our clients' customers' data set. And you can see here that this would be kind of like the root level of a Mongo document, which is like a nested key value store, right? And then this is a key with a bunch of values in probably an array. And then you have sub-documents here that kind of branch out in different ways. And so basically we take that and turn it, extract the time series data from it and turn it into basically like matrices, right? SQL-like data. And there's a really cool tool that someone on our team, Jeremy Stanley, wrote to do this. It's called TidyJSON, which will be later. And then from there, we take these time series and we do all sorts of transformations on them to extract features that go into a machine learning model. And then basically with that matrix, we take it, split it into training and test, the standard machine learning things, and then apply gradient boosted machines, GBMs, on our training data. And then, there's a process of cross-validation and grid search to find hyperparameters and tune the thing. And then after we have that, we generate our predictions on users. And we run A/B tests to evaluate, we evaluate lift on the test set from our models. Then we rebuild models on all data, and finally we make predictions for users. And then there's a process of running A/B tests on these predictions to make causal inference and answers. So doing all of this has a lot of computational challenge, right? There's the feature engineering component, there's running many dependent job scale, the resource allocation, auto scaling. So because the title of this talk was about the three things: problem formulation, optimization, and infrastructure. And because I said that the first two kind of a little bit more talked about, I'm going to focus on some of the infrastructure things that we've done. So specifically, I'm going to talk about Stolos, which manages task dependencies in a directed acyclic graph. It's actually a directed acyclic multigraph. And then this cool autoscaler that minimizes the difference between error in a metric. So we'll talk about those. So here's Stolos. All of these are open source, so you can check them out online. And if you're confused, you can ask me later, because I'm going to go probably quickly through this, or you can read the README also, which is really good, I think, if it's not only an issue. So what problem does Stolos solve? So basically, the problem Stolos solves is when you have these tasks, right, and you have task A and task B and task C, you can only run task B until A runs. You can only run task C until A runs, but B and C can run in any order. So this is a really common problem. There's a lot of tools to solve that very simple construct, but there are not tools to solve a more complicated construct for this that I will show you in the next slide. So we figured out how to do this, and then we basically have this concept of a queue that says if you can consume from the items in this queue in any order, and you basically remove the problem of having this dependent task structure. So here's an example of what our infrastructure looks like right now. So one way to look at this is we have this very simple branch of our pipelines. It's part of a different graph. But basically, like, this represents a group of applications, and this represents another group of applications. And what happens is application 1 runs with all of here, and then it splits into many kind of subtasks, and then all of those subtasks join, and they split and they join. And you have a dependency structure that is pretty simple like this, right? Map reduce, map reduce. And then you do this a couple times. And each little node here is doing something different. So it's a variation of a task, and it's an instance of one of our applications. And then you have this logic where you're doing something similar here, but you're kind of joining subsets of this work to one node, and joining subsets of this to another node, and then taking that, using it to generate, to define our pipeline, generate work that can be done. So this is a complicated process because it happens every day. That picture popped up in here. There's some kind of bug in Google Docs. Every time you copy the slide, it goes nuts. But basically, each day is independent of previous days, and you can change that in the structure by basically combining these different days together at the root node, and you can end up creating, I think, a streaming system from a batch system. So I should have said earlier that the way we've designed our predictive modeling sightlines is as a batch process, right? Every night you train a bunch of models and do some predictions. The next day, you train a bunch of models and do some predictions. So with a system like this, I believe that we'll be able to convert the period of time over which we're training into smaller segments and create a real-time, or at least near real-time training for this, and then the prediction system can be different.
Quick question.
Yeah.
By multigraph, do you mean there are multiple edges between parameters?
Yes. So a multigraph is basically a bunch of graphs in the same like space, right? So they might not. So if you imagine that this is all one connected graph, and then the one behind it is another connected graph.
Yeah.
The two of them together makes a multigraph. So it also happens that we have, a graph here and a graph here, but within this plane, there's actually a couple different subgraphs that are independent of each
Just
other.
something like hypergraph, where you can have multiple edges which are timed.
I don't know what that is.
Okay. There's something I read somewhere.
Similar to
Yeah. Okay.
Cool. Yeah, so if you have questions, any more questions?
So are the vertices the same in every one of these graphs?
No, so every vertex defines a unit of work. And the way that that work is defined is by this concept called the job ID. Basically, you'll have to read the README to understand what I'm about to say. But basically what that means is a job ID identifies how your work is changing from hop to hop through this graph, through this directed graph. And so if you look at your job ID, you immediately know how it's connected to its neighbors.
So is this basically just creating a hierarchy for queuing jobs that are depending on each other in such an order that it always stalls until the data it's waiting for being processed by a different job is ready? So it pipelines everything into like one pipeline, but it's just everything's at a different stage of the pipeline and waiting for previous input to catch up.
Yeah, so I think if I understood everything you said, I think yes. Okay. So you're pretty on there. You're basically just taking a bunch of a dependency structure and flattening it so you can run it in any order. You try to do that. And then this happens for just under 500, or we have 500 clients. Like right now, how many models? A lot of models, and there's a bunch of. It's very, very parallelized and distributed and complicated. I can't remember. So go ahead.
So the dependencies are defined by the models themselves, not by the data, correct? Like you have a model or a job that you're going to run. You know that like this job relies on data being pushed in from a different source, which relies on another job. So like the dependencies are something you control in a way by the models you're choosing, right?
Yes and no. So you can define, basically what I think you're confused about is the idea of how to, like a dependency, the concept of a dependency is decoupled from your application or from your data.
Okay.
And it's just a matter of which one you would prefer to apply it to. So if
Okay.
you want to build a system that is, defining dependencies based on the structure of your data, that's one way to do it. The way we've actually implemented it is the latter, where you can kind of switch between it very seamlessly in Stolos, because you're just using this concept of an ID. But we primarily use the concept of a model, client ID, and a date as most of the identifiers for how work is changing through our system. Oh, lost that again.
So what possible like amplification of error could a pipeline like this cause? Since everything's based on like previous like dependencies, is it possible that like, it might be like oversimplifying this, but let's say your previous model had like a certain bit of like error bound, like could you basically use the structure and also bound the error on the overall like full job when you flatten it out based off like how much each dependency is factoring into the overall model?
I'm not sure I understand.
So these different jobs are like different stages. So they're not like a machine learning thing. So there's no concept of an error exploding.
But like,
so the jobs are something like feature engineering, a lot of feature preparation.
yeah.
The only thing that can happen there is either the job won't run or the job will run.
Oh, so it's just objectively transforming data. They're transformation jobs, not necessarily like model parameters or like
No.
learning or like
Those are
classification.
part of a separate job where we're doing like a grid search and we parallelize the grid search.
Okay.
And there are no real errors that can happen there. So
Okay.
we don't have to worry about that right now.
One way to envision, to see this is like the way that we're currently using it, right? You have a application that takes a bunch of parameters for it to run, and those parameters change every time you run it, right? So if you're training 50 models, the cross product of 50 models and 500 clients, you basically like multiply those all out and have all of these things that are each depending on potentially very different parents.
Yeah.
And so Stolos basically figures out what the parameters are for this particular instance of the application.
Okay.
And then it will also figure out how to run them all kind of in parallel. So that's a problem solved. Okay, good? Cool, good questions, thanks. So the next one I wanted to talk about was this tool called Relay, and then also relay.mesos. So, are any of you familiar with what Mesos is? So, okay, seeing yeses and nos, which is good. So Mesos is a really cool resource allocator, more or less. And what it does in many ways is they advertise it as a kernel for distributed systems. So what it does in many ways is it pools all of your resources together and treats them all as kind of one big resource pool, and then lets you basically run your applications on top of this resource pool. And it deals with what happens when resources go away and jobs need to be restarted and all of these really complicated problems that arise. And one thing that's neat about it is it also leaves a lot of the decisions about how to schedule your jobs to your Mesos frameworks, they're called. So relay.mesos runs on Mesos as a framework, and it basically uses Relay to auto-scale jobs. So what does Relay do? So if you imagine you have a time series, like a signal over time, a sound wave is actually an example of that, right? And then you imagine you have a target signal over time. So what Relay tries to do is minimize the difference between the measured signal and your target signal. And this is actually a really hard problem. It's the one that thermostats have to solve, right? So if you have the temperature in a room over time, and then you have like a target temperature, which is a flat line, usually, it can add a little heat to the system, right? And then because it's an eventually consistent metric, you will, if you keep adding heat at an equal rate until you get to this, you'll stop adding heat, but then by the time the heat travels to your thermometer, you'll be like way out here, and then you'll let it drop, and you'll kind of eventually maybe stabilize. Sometimes you don't. And this is a really interesting problem and also very hard to solve. Well, I don't know. I thought it was pretty fun to solve the way I did it. And then relay.mesos plugs this into Mesos. And so the way we use this is we basically use Relay to manage these queues generated by Stolos and consume from them. So here's what so now I'm going to try to explain in this amount of time how Relay works. So if you imagine you have a signal, right, and it looks something like this, you can take any signal and break it down into its component frequencies. So what that means is, right, this one has a sine wave, component sine wave. And what it means is this one has a sine wave that looks like this, but it also tends to have a sine wave that looks like this, right? And then it has this one and this one. And it expresses each one of these in different, different energies, right? So there's more of this one maybe than this one. That's what a Fourier transform does, okay? And then if you were to say, what if I took this signal, represented it as, sorry, I'm gonna point this way. What if I took this signal, represented it as its component frequencies, and then for every frequency, found where I currently was in time, right? So you're sampling a signal at every second, and you say, I'm at this second. And then you say, for this frequency, look back a whole period, right, of this wave. I've sampled this period here, 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 here. And the idea is that if you can find the error between each wave between each period for every period, here, here, and here, and then take a basically sum of the absolute value of these amplitudes, you can come up with an estimate of where this signal should be right now. So then if you use that, so basically that's the idea. So I'll explain how that fits in to Relay's algorithm. So Relay uses this known about thing called a PID controller. Did I? Okay. So a PID controller, sorry, I should have messed up my slides a lot. A PID controller looks at the current position. So you have the signal in time, right? You have the current position, you have the integral over time of that position, and you have the derivative. So, right, how it's changing in its past history of errors in the current position. And then it takes a weighted sum of those, where your weights are determined by some tuning algorithm, to identify how much heat you should add or coolant you should add to your room to maintain the temperature. And so what I did to this equation was drop this term, which a lot of people do, because it can be noisy, and then make this to 1, which not a lot of people do, and then put all that magic that I talked about in this slide into that Ki value. And then basically what happens is when you configure the algorithm like this, and I'm kind of skipping over a lot of the math, because if you want it, it's on GitHub. It will basically create a feedback system that converges and continuously minimizes the difference between your target value and your current signal. So this is an example. This is like, you can use Docker to run one of the examples, and this is what it looks like for this kind of signal, right? So if this is, if this blue line is the current signal, and then this purple line is the target, it's pretty damn good. And that's very hard to do, I found. So that's a little bit about how Relay works. And thanks. So yes.
So I'm a little confused. Why exactly do people drop the differential term in the PID algorithm? Like, I understand there's noise, but couldn't you use some sort of filter to smooth out that noise a little bit?
There are a lot of different ways. So there are a lot of different ways to do this, right? So the simplest would be to drop both these terms and just look at the current position. Okay, that was the first example I showed with temperature, where you just keep adding. A variant of that would be to set, a weight that says, well, if this is the difference in temperature that I need to add, just half that every time. So what ends up happening, hopefully, is you won't overshoot. But however, in systems like that, you ultimately end up either overshooting or getting into certain states where the temperature is just too cold and you'll never make it. If you keep adding at half this rate, by the time you add and then add again, you'll just stay down here. You'll never make it. So what people do to do that is try to add, this term and that term. And if you look at the error history, if you know that you've been off for a little while, that helps you. And then it turns out that you can also look at, how you're currently changing. But if you think about being down here and going up and going down, right? When you're going down, that change is going to have an equal effect, a magnified effect as to when you're going up. And it's just noisy.
So
I don't understand how to.
why don't they model it as an inertial mass type problem? Is my question. Because isn't that what it essentially is? You have an increase in some sort of variable which you're measuring, that's your signal. But the thing is, you don't know how quickly that variable will rise above or below your target signal value. So I guess wouldn't it make more sense to target a physics problem and this is completely could be naive
You can think of that as white noise. So it's if you're fitting on the linear regression line, you can't really track the line. You always fit a line. So that term is kind of noisy like that. So essentially you're taking the mean value of that instead of trying to track that error. You could try to track that error, but you probably end up overfitting and a lot of weird stuff may happen. And you should probably see that happen.
Okay.
It's hard to tune a derivative, but I I haven't done any like proofs under this, but I would imagine that you might be able to say somehow that I've incorporated this. It could be possible that this could actually be incorporated in this term.
But
You
you
look at
require
that delta,
data.
it's SP minus PV, so your current position minus previous position, and you're assuming that doesn't change.
And this is the mechanism you are using to upscale your Mesos cluster. And what are you measuring as an aggregate, like in terms of the load of the cluster? I mean, what is that variable that you are using to do the upscale?
Oh, that's a very good question. So our implementation currently tracks the size of the particular queue that it is auto-scaling. So it's a really simple implementation, right? You have a queue and you just need to keep running consumers until it's 0. There's another version of this we have that I'm about to implement that says, you can only have consumers on during certain periods that are based on either arbitrary hard-coded rules or dynamic rules. And then the target signal would be the current value of the queue or 0, right? You can do a square wave like that. And if you want to, so right now we're just doing queue sizes. The GitHub page has a few examples for how to do other ones. Any other questions?
So how do you exactly grab the target, or like, because like I'm assuming like since this is all real time, you're not really gonna know how many incoming jobs are there for like a given queue like in a few minutes. So how exactly do you figure out like what's your target? I'm sorry if he just asked a similar question, but how do you figure out like where I want to be if I have a queue with like, let's say it's like X plus delta. I know it's going to be some delta increase, but I don't know exactly how much. So how do I pick the target value for that delta?
So that's also a good question. So the idea of Relay is that the metric you're monitoring is eventually consistent, right? And what that means is if you sample right now, it might not reflect, what the actual value is, or it might not reflect what it will be the next second. It could be very different. But if you break down the signal into these repeating components, you can predict what that's going to be or what that's supposed to be.
So analyze past trend behavior and use that as a model for what expected future behavior will be?
Yeah. And so basically what you're doing is you're taking the signal, decomposing it, and then reconstructing it, right? And when you do that, you have this kind of idea of what it should be and then what it actually is. And when you have that difference, you just kind of decide how much of that difference you're supposed to act on.
Okay. And I realize for signals, it's like a bit of a different, because this is just like an analogy for a constant you apply to like any problem that has some sort of queue size or any sort of like allocation resources. But like when you're sampling like for signals, like let's say you're working with ACO-like signals, what, like I saw you used FFT before. Is there like a difference between like using FFT versus DFT for this? Or like using like a wavelength transform or like different versions of Fourier transforms?
I just used an FFT for this.
Okay, sorry, I'm just curious.
I didn't really, I didn't really try like an extensive array of all possible options. If you want to, you should totally do it.
Because like one thing I'm thinking is like discrete cosine transforms are usually good for like measuring deltas between like a series of values from what I understand. So like could you do your approximation of like actual increasing behavior or deltas?
Probably.
I think it depends on the kind of signal that's coming in. So you could do a lot of optimization there.
Yeah. So the short story is I don't know, but it'd be awesome to try to figure that out.
Okay.
Yeah. So yeah, this is a really simple library. It's on GitHub, and you can see they're all at /GitHub group /whatever. This is where the math component stuff that we just talked about is, and then this is like just an implementation of that actually has some pretty I would argue significant problems with it, but it actually works really well. And then, given that it has some issues, and sorry for that, that should be relay.mesos. And these are some of our other tools. Cool, and then, yeah, I don't know if you guys have other questions about Mesos or about our tech stack or whatever, feel free to ask. We're here.
Yeah, so this is independent of your presentation, but how you manage is a problem in my past. So how you manage quotas for your team? Like for example, you have these hours or this budget in Amazon Web Services to use. That's number one. And the second is if you want to test a new tool, how are you deploying your test environment with Chef or Ansible, or what are you using in your team?
So we don't use quotas, but every one of our applications via relay.mesos is converted into a Mesos framework. So basically what it does is it takes a bash command and converts it to a Mesos, like an auto-scaled Mesos framework. And there are some problems that we've run into with frameworks resource, framework sorter. Are you familiar with this at all? Okay, so basically there's an algorithm that decides how many resources to offer to a particular instance of a framework, right? To a particular framework. And then that framework decides whether or not to take the offer for resources and use it to run its jobs that it has outstanding. And there are all sorts of really complicated issues that we found when that, because frameworks were getting starved out, because some of them had requirements for a lot more parallelism than others. So the ones that had a lot more parallelism weren't getting the resources they needed, and then their queues were getting large, and then all the dependent tasks, which had small or zero queues, were getting all these offers, but they couldn't do anything. So that was, I don't know if that answered your first question about quotas.
Yeah.
Okay, and then the second question, what was the second question?
Is about deployment. Like you already mentioned that already.
So the question is, right, how do we test our changes? How do we deploy things? So we've done this kind of nuts and really awesome thing with our infrastructure. We have a development environment, and then we've made an exact copy of every single part of this and made a production environment. So that way we just trash the hell out of our dev environment all the time, completely break it, like spin up 100 machines, turn them down to 0, we'll do whatever we want. And then once we stabilize, we push it to prod.
And what is the tool you are using for deployment, Chef or Ansible?
So we have Chef, well, we have a lot of tools. So we have Chef to manage our the actual slaves, Mesos slaves, and our boxes, but then our applications are managed through a deploy script that I haven't open sourced because I'm not sure that I want to expose it to everybody. It's a cool tool, but people will just be confused, I think. Yeah, so the way we do it is the two environments. Thank you. Yep. Cool. All right. Thanks, guys.